Okay, anybody have any homework questions you want me to go over? All right. Yes.
I think I have one from Monday.
Okay. Yeah.
One second.
Is it circular motion?
I think so.
Okay.
Or, I mean, the one that was due on.
Okay. $11?
Yeah, I didn't know.
Okay.
I think it was just one part of it.
Well, let's just go through it. I'm sure there's lots of people who would like, a little refresher, and it has a lot of good stuff in it.
I think it was for A, I got a positive 3.23.
Okay.
And then on the problem solutions, you got negative, I think.
Okay. I know there's still some things like that in my problems here and there, so I would not be surprised at all. Let's figure it out. Yeah. All right. So we have this incline. It's at 20 degrees. The hanging mass is moving down at this instant. Okay, so this is a problem where the accelerations of the two bodies are different. So I'm going to pick one of these to start. Doesn't matter which one. And on this body, I'm going to use the coordinate system like this. And on this body, I'm going to use a regular coordinate system. So on the 5, we have the weight, 49.05. We're starting out with no friction, so there's a normal force like this. There's no friction force, and the pulling force from the cable is away from the body.
Sorry, I know you're going to help me, but I meant on problem on numbers. Oh gosh,
letter
C. I got positive 0.92, and you got negative 0.92. That's what
okay.
I meant. Yeah, I got that too.
Okay, that sounds very suspicious then. All right, so well, once we do the first part, the other ones will be fast. So I'm just going to go through them all, I think. So the weight force, that's the first thing we have to figure out is the angle. Our coordinate system is like this. The weight force is straight down. This angle is 20 degrees.
Oh, your projector isn't.
I'm like talking like you can see it. It's always something. What if my computer wasn't on either? Okay, that's better. So the weight force is like this. So we have to figure out, we know it's going to be either 290 or 250 degrees for the cosine and sine. This one, if you start at x and go around, it's 270 minus 20. So this angle is 250. Newton's second law then says 49.05 times the cosine of 250, 49.05 times the sine of 250, plus t0 plus 0n is equal to the mass times the acceleration. This thing's moving along the x-axis, so there's the acceleration. Bless you. So this says negative 16.78, negative 46.09, plus t0, plus 0n is equal to 5 times a0. So t, if I rearrange the x equation here, it says t minus 5a. Why am I doing it this way? Because that's how I do it in my engineering classes, but I'm doing it differently here. So t is equal to 5a plus 16.78. And we don't really have any use for the y equation for part A. So now I'll set that aside and go to the second body. The free body diagram, you have a weight force down. This is also 5 kilograms. A pulling force up from the cable. So Newton's second law says 0t plus 0, negative 49.05 is equal to 5. And now we have to think about the acceleration of that hanging mass. If the 5 kilogram goes in the positive x, an inch, well, they're both 5, but the hanging one will go an inch down in the negative y. So I'm going to write this as 0, negative a. And this time the x equation doesn't help, but the y equation says t minus 49.05 is equal to negative 5a. And I'll substitute this first equation into the second one. So we know that this is equal to t. So I'm replacing the t in the second equation with this. And then minus 49.05 is equal to negative 5a. We get 10a is equal to 32.27. So A is equal to 3.23 if you round it. We're looking for the acceleration of the block. I guess I'm talking about the one on the incline. So I'm going to plug that into this vector. And you get that the acceleration vector is 3.230. or in other words, this way. Okay, so in this problem, when there's no friction, the acceleration is up the ramp and the hanging mass is accelerating down. At the instant shown, that's the direction they're moving. So you have the velocity and acceleration in the same direction, so it's speeding up. And now, okay, tension, you can plug that back in. I guess maybe I'll skip that and go to the part C. So now there's a friction coefficient of 0.5. So the free body diagram of the block, there's a weight force down of 49.05. A normal force. A friction force, it says that the block is sliding up the ramp, so the friction force is down the ramp, and it's equal to, the magnitude is 0.5 times that normal force. And then there's the cable tension. So Newton's second law, the weight force is exactly the same as it was in part A. So that's negative 16.78, negative 46.09, plus T0, plus 0n, and then negative 0.5n, 0 for the friction, and that's equal to 5 times our acceleration, and it's still sliding along the x direction, so that's what you get. And this time we have to use the y equation to find n. So n is equal to 46.09. And then plug that into the x equation. And so from this, I'll arrange it as t is equal to um, 5a plus 6.27. And then go to the free body diagram of the other one. Zero t plus 0, negative 49.05 is equal to, for the same logic as before, this has to be 0, negative a. And so the y equation says t minus 49.05 is equal to negative 5a. I'll substitute that first boxed equation into the second one. So we get, yeah.
Would it be 6.27 because it's negative 16.87?
I moved it to the other side of the equation.
Yeah, it's
Oh, so yeah, I should add them. They're both negative. Thank you.
yeah.
Okay, let's try this again. 0.5 times 46.09 plus 16.78, 39.83. Okay, so 5a plus 39.83 minus 49.05 is equal to negative 5a. So 10a is equal to 9.22. And so A is equal to 0.92. And so the acceleration vector is 0.920 or that. That's what you got?
Yeah.
Okay, well, good. And then it's still speeding up, but not as much because of the friction. Any other questions about that one? Or any other homework questions? Okay. So now we're going back to circular motion. So remember that we're sort of dividing up all circular motion problems into two approaches. So what approach you use depends on whether it's a tetherball problem or not. And so you need to be really clear about what a tetherball problem is, because there are things that look a lot like it but aren't quite it and whatever. So a tetherball problem is this. The only contact force on the object is a cable or a string or a rope. And the object is rotating in a circle that's parallel to the ground. So the object is swinging around in a circle that looks like this. And the only thing that it's touching is the cable. So a couple things that are kind of, you can think of them as close to being tetherball problems, but they're not, is like this one where the thing is in contact with the ground. And then the other one that I did an example like this at the end of class last time. I really only do these problems because I like drawing that picture of the hand. That's not true, it's for physics. Okay, so if this thing's going that way, you know, like the height is changing as it moves. This is also not tetherball because the circle isn't parallel to the ground. Okay, this one is. Okay. One important fact about tetherball problems is if we're ignoring air resistance and any kind of friction, you know, we're assuming a lot of things that can take small amounts of energy away. We're ignoring those. One important fact about these tetherball problems is that they're always uniform circular motion. Who remembers what uniform circular motion means? Yep, the speed stays constant the whole way around. And if the speed is constant, that means that there's no tangential acceleration. So you can think of it as like the total acceleration is just equal to the centripetal acceleration. Okay, so I said that for every other kind of problem, you want to choose a view where the circle is visible. Okay, so like if you're using the other approach, if you're looking at a circle that's parallel to the ground, you want to take a top-down view on it or from the bottom looking up. On this one, the approach is a little different. So here are the general steps for tetherball problems. First, take a side view. With the ball on the left of the attachment. So that's like the picture that I drew here. You're going to think of the problem this way. So that's, 90 degrees from the way that we would think of this problem if it wasn't a tetherball thing. Second, draw the centripetal acceleration horizontal toward the attachment point. Okay, so in this problem, you've chosen this view. The centripetal acceleration is always horizontal, and it's toward the center like this. Third, the magnitude of the centripetal acceleration is v squared over r. And r now is let's calculate it as L times the cosine of this angle theta, and I'll draw the picture with these in. So this is the angle theta, and the length of the cable is L. Okay, so that means that this is the R vector in V squared over R. So that just comes from SOHCAHTOA, from trigonometry, calculating that radius R. Now, free body diagram. And then Newton's second law. And you're always going to solve for the same two variables. You're going to solve for the speed V and the cable tension T. So I'm going to do an example going through all those steps, but does anyone have any questions before I start that? Yeah. Yeah. Okay, so yeah, the free body diagram would be, there's the ball or whatever it is, there's the weight acting down, and then there's a cable tension like this. And it can't ever be different than that because that cable is the only thing touching the ball. Okay, so let's say we're given that this angle is 45 degrees and the length of this string is 0.25 meters. And let's say M is equal to 0.1 kilograms. And we want to calculate the cable tension and the speed. All right, so the first thing we have to choose is a view, and that's already done for us. And the centripetal acceleration points this way. Yeah, that T is the cable tension. The magnitude of the centripetal acceleration is V squared over R. R is equal to 0.25 times the cosine of 45 degrees, which is 0.177. And so the centripetal acceleration magnitude is V squared over 0.177. Okay, well, what's the centripetal acceleration vector then? The centripetal acceleration vector is pointing in the positive x direction. So this is V squared over 0.177, 0 for y. Yep.
Cosine of 45, I got 0.7071.
Yeah, and then multiplied by 0.25.
My bad.
Yep.
Sorry.
And so now we'll do the free body diagram. The weight force is, so the mass is 0.1, the weight force is 0.1 times 9.81. The cable force is this way. And now Newton's second law says, okay, this T is at the same angle as the cable. So that cable force is going to be T times the cosine of 45 degrees, T times the sine of 45 degrees. Then add the weight force. And it's equal to 0.1 times what we calculated for that centripetal acceleration. So I can rewrite this as 0.707 T, 0.707 T plus 0, negative 0.981 is equal to 0.1 times V squared over 0.1770. And now we'll use the y equation to solve for t. So T is equal to 1.39 newtons. And then we can plug that into the x equation. So 0.707 times 1.39 plus 0 is equal to 0.1 over 0.177 v squared. Okay, so v squared, if you multiply and divide all these together, is equal to 1.74. Take the square root. And you get v is equal to plus or minus 1.32 meters per second. This is a speed. It has to be positive, so we'll take the positive one. Any questions about that? Yeah.
So in the x equation, we have 0.707 t equals 0.1 times v squared divided by 0.177. How do we go from 0.1 times v squared divided by 0.177 to 0.1 divided by 0.177 times v squared?
Oh, well, with multiplying, you can move those around. The order doesn't matter at all. So no matter how you write this, you can think of it as you have a 0.1 and v squared and a 0.177. And you can think of it as 0.1 times v squared over 0.177 or 0.1 over 0.177 all times v squared. Is that what you're asking?
Yeah.
Yeah, just like, let's see, you know, 3/2 times 6, you could write as 3 times 6/2. It doesn't matter what order you do that in. Any other questions? Okay, intuitively, what do you think would happen? So let's do this question again, but let's make that angle smaller. So if that angle that's 45 right now was 20 degrees, that would mean that that ball had to be higher, right? What do you think is going to happen if this ball is higher to the speed and the tension? Do you have a feel for that? The tension will go up and the speed will go up. Like you can think of it as like if you start this thing spinning really slowly, that angle is going to be, it's going to be hanging really close to this pole. And so that angle is going to be really big, close to 90 degrees, if it's going slowly. And then as you spin it faster and faster, this thing is going to rise up. It's like that swing ride at Valley Fair, you know? It starts out and they're just hanging, and then the faster it goes, that angle gets smaller and smaller. Okay. Who's with me on that? Who likes Valley Fair? It's great. So we're going to do this calculation again, but we're going to make this angle 20 degrees, and we're going to see that the speed and the tension are both bigger. If we made this angle 85 degrees, then the tension would be very close to just the weight of this thing, which is the biggest it could get, and the speed is going to be really low. And how fast do you think it would have to spin around for that angle to reach 0 and be horizontal? The answer is it'll never do it. So basically it's like a limit as that speed goes to infinity. Okay, so there's always going to be some angle there. And if that angle is 1 degree, it's going really, really fast. Okay, so we're going to do the same setup, but the angle is 20 degrees. And from just thinking about this physically, we expect that T and V will both be higher. So now we're doing a problem like this. Okay, so the view we're going to take is like this. The centripetal acceleration is this way. The magnitude of the centripetal acceleration is v squared over r. And r is equal to, so we still have the length of this cable is 0.25. So r is 0.25 times the cosine of 20 degrees. And this time we get 0.235. So the centripetal acceleration magnitude is v squared over 0.235. So the centripetal acceleration vector, this is in the x direction. So v squared over 0.235 for the x component and 0 for the y component. Now a free body diagram of the ball. The weight is still the same, 0.981 newtons. The cable tension is that way. So Newton's second law says T times the cosine of 20, T times the sine of 20, plus 0, negative 0.981, is equal to the mass times the centripetal acceleration So the y equation says sine of 20 degrees is 0.342, so 0.342 t minus 0.981 is equal to 0. So t uh, 0.981 is equal to 2.87 newtons. So you can see, compared to the 45-degree example we did, that's about twice as big of a tension, 1.39 in the last case to 2.87. And now plug that into the x equation, and you get cosine of 20 is 0.940 times the t that we just solved is equal to 0.1 over 0.235 times v squared. And so v squared is equal to 6.34. Take the square root. And v is equal to plus or minus 2.52 meters per second positive. And that speed is also higher than the speed we got here of 1.32. Any questions about that? Okay. Well, that's all I was planning to say about circular motion. So I'm just going to go into the next topic. So the next thing that we're going to talk about is conservation laws. Conservation in science means some quantity stays the same through time. So some quantity, let's say, stays constant in time. We're going to talk about two conservation laws, and they're pretty different. The only thing about them is that there's some quantity that we can assume is not going to change. The first one is conservation of linear momentum. And leave a little space here in your notes. I'm going to write the second one down, and then I'm going to say a little bit about each of these. The second one is conservation of mechanical energy. Okay, and now, kind of for the first time, we're starting to get into approaches, or we're starting to get to where you can look at a problem and it's not totally obvious right off the bat what approach you want to use. There's maybe a couple different ways you might think it would make sense to go about it. So I want to try to, make it clear what you should look for to say, okay, I'm going to use conservation of linear momentum, or no, I'm going to use Newton's laws or whatever. Conservation of linear momentum, this one is pretty straightforward. You will only use this in problems that involve collisions. If there's a collision in the problem, you're going to use this for the collision. And if there's not one, you're not going to use this at all. Okay? It's also useful for explosions, by the way. I don't think I have any problems like that for you, but that's another thing that you could use this for. Conservation of mechanical, forgot to write energy. Conservation of mechanical energy. Well, you've all heard of conservation of energy, and that is always the case that energy isn't destroyed or created. Mechanical energy is a type of energy, and under certain conditions, we can simplify this very complicated conservation of total energy into just thinking about the mechanical types of energy. So you can think of this as like a subset of conservation of energy. And this is going to be useful when you're trying to find a relationship between an object's position and its speed. So it's useful when looking for a relationship between an object's position and its speed. The thing that's can be a little confusing about this is you can also use the constant acceleration equations to find relationships between positions and speed. And so it's not always like super obvious when this is the way to go, but I think once you do a few problems, you'll start to get used to what kind of things to expect. One thing about this that's different than the, so this is like one key hint. If you're using constant acceleration equations like we've done up until now to find a relationship between position and speed, you have to know what the path of the object is. So if you see a problem where it only talks about the position and speed at one point, at one instant, and the position and speed at another instant, and it doesn't tell you anything about what's happening in between, you're probably going to be using conservation of mechanical energy. Okay, so one key hint is if the problem doesn't specify the path between the two instants, then you're probably going to use conservation of mechanical energy. Well, you haven't seen any of the types of problems we're going to do yet, so this doesn't mean a ton to you yet, but go back to these notes as you start doing the problems and start seeing if you can recognize these things, okay? Okay, so we're going to start with the quicker and easier one, conservation of linear momentum. And it says, well, so remember, this is just like, how do you recognize whether to use this? It's just collisions. If you're talking about two balls running into each other, two objects smacking into each other, a bat hitting a ball, those are the kind of things where you'll use linear momentum. And so first we have to define what linear momentum is. It's a vector quantity, and I'm going to denote it with a lowercase p, which is kind of a bummer because we already used that for position. But, you know, there's only so many letters. And it's equal to the object's mass times its velocity vector. So m is the object's mass. V is the object's velocity vector. The units you can get from that definition, it's going to be units of mass times units of length divided by units of time. And because of that, the SI units for linear momentum are kilogram meters per second. And I want you to notice two things about this. Keep two things in mind about linear momentum. The first one is that this is a vector quantity, so it has a magnitude and a direction. when we talk about energy, we'll see that that isn't a vector, it's just a number. Energy doesn't have a chosen direction or anything, but momentum does. And it's always in the same direction as the velocity vector, okay? So P is a vector, and it's in the same direction as the velocity vector. And now, like intuitively, what can you say about what momentum means? The magnitude of the linear momentum tells you something about how hard an object would be to stop. Okay, so let's think of something with a really big magnitude of linear momentum. A train, you know, has a huge mass. It's going 50 miles an hour or whatever. Would you want to try to stop it? No, you know. On the other hand, like a snail has very little momentum. It has a very small mass and it's moving really slowly. Yeah, sure, you'd happily pick that up and move it to another part of a garden or whatever, you know. So that's what linear momentum tells you, okay? It tells you how much you want to get in front of something. So conservation of linear momentum says that if there is zero net force on a set of objects, so let me say it like this. Choose a group of objects with no net external force. Okay, so they can apply forces to each other, but they just can't have things outside of that group of objects applying forces to them. So they can apply forces to each other. But no outside forces act on them. Then, if you add up the linear momentum of all of the objects at one instant, and I'm going to call this before the collision, that's equal to the sum of the momentums after the collision. Okay? Any questions about that? Okay, so I'm just going to do an example. Mathematically, this is a pretty easy thing to apply. So let's say that we have two train cars moving toward each other. So let's say that the one on the left has a mass of 2,000 kilograms, and it's moving at 3 meters per second. And the one on the right has a mass of 4,000 kilograms. And it's starting at rest. So I guess really the 2,000 is just driving into the 4,000. If after the collision, the 4,000 kilogram car is moving to the right at 2 meters per second, what's the velocity of the 2,000 kilogram cart after the collision? Okay, so first we have to think about, in our chosen view, in our chosen coordinate system, are there any forces other than contact between these bodies that's acting on our system? The weight is acting into the page. This is like a top-down view, you know. The normal force is acting out of the page, but in this view, in this top view, there are no forces acting on these other than them hitting each other. And so we know that we can apply this law. And so before the collision, we have a mass of 2,000 kilograms times the velocity of the 2,000, that's moving in the positive x direction, so 3, 0. And before the collision, the 4,000 kilogram cart has 0 velocity, so that is no momentum before the collision. And then afterwards, we know that the 4,000 kilogram car is moving to the right at 2 meters per second, so that's positive 2, 0. And we want to know what's the velocity of the 2,000. So I'll break it up into x and y components. Okay, well, the y equation is easy. It says 2,000 times 0 plus 4,000 times 0 is equal to 4,000 times 0 plus 2,000 Vy. So Vy is equal to 0. That seems pretty obvious that if they're all moving in one direction, they're going to keep all moving along this same line. The x equation says 2,000 times 3 plus 0 is equal to 4,000 times 2 plus 2,000 Vx. So 6,000 is equal to 8,000 plus 2,000 Vx. Subtract 8,000 from both sides, and you get that, so negative 2,000 is equal to positive 2,000 Vx. And so for this collision to happen this way, the 2,000 kilogram train car needs to have an x component of negative 1 meter per second. And so the total velocity of the 2,000 is negative 1, 0. Or in other words, it's moving 1 meter per second to the left. Okay, so that's conservation of linear momentum says if we know that after the collision, the 4,000 is going 2 meters per second to the right, the only possible velocity for the 2,000 kilogram car would be 1 meter per second to the left. Okay. I want you to notice one thing about this example. We couldn't have done this problem without being told something about what's happening after the collision. So without being given some information after the collision. The information that I gave you in this example problem was what the heavier train car was doing afterwards. And the reason that we couldn't have done it without that information is that clearly when you think about it, like what are the velocities of these things going to be? It depends on how that collision happens, you know? Like what if these two things are made out of Jell-O, you know? They'd smash into each other and stick together, right? Or just clump into a blob. But what if they're made out of something bouncy, you know, like pool balls or whatever? They'd hit each other and bounce apart. And so you have to know something about the collision, okay? You have to know something about the nature of the collision. Well, there are a lot of ways that these collisions could happen, but we're going to choose the one always. I mean, the one that we're going to do in this class is the one that's easiest to do mathematically. It's no different conceptually, but it's easier to do mathematically. And so we're always going to do problems where the things stick or latch together after they collide. Okay. So we'll always do problems where the objects stick together after the collision. So what does that do for Let me tell you the name of that too. So these are called inelastic collisions. Elastic means that the things bounce back to their original shape after they deform. And so if the things stick together after they collide, that means that they're going to have the same velocity as each other after the collision. And that means you're only trying to calculate one velocity vector, okay? So this means the objects will have the same velocity after the collision. So let me just quick redo this example that I just did, but we're going to assume that the train cars latch together after. You know, they didn't latch together the last time. One went to the right and one went to the left. So I'm going to draw these two things again. We're going to start with the 2,000 kilogram train car moving, what was it going, 3 meters per second? And it runs into the 4,000 kilogram train car. If they latch together, on colliding, what's their velocity after the collision? So we're going to set this up the same. So we have a 2,000 kilogram train car that has an initial velocity of 3,0, and a 4,000 kilogram train car that has an initial velocity of 0. And then after the collision, now since they latch together, we can just think of it as a single object that has a mass of 6,000, you know? And we want to calculate the components of its velocity vector. The y equation again says that Vy is equal to 0. The x equation says 2,000 times 3 plus 4,000 times 0 is equal to 6,000 Vx. So 6,000 is equal to 6,000 Vx. So Vx is equal to 1, positive 1 this time. So after the collision, they're moving with a velocity of 1, 0, or moving to the right at 1 meter per second. Any questions about that? Once you've done a couple of these problems, they're all just the same, you know. And then I'll probably on Monday do an example or two like this, and then we'll get into the one that's a little more involved, conservation of mechanical energy. Okay, anybody have any questions? All right, that's it.